Hello, students. Today is the end of an era. Today I have retired my old set of headphones, and if you look, you can actually see they have worn off. All of the fake leather has come off. I mean, I had my name on them. I had these from the beginning of the pandemic. They made it this far, but after the last set of videos, I had pieces of them on my face when I went downstairs, and my wife said, "What is happening to you?" So, good job, and Godspeed to your next life. Hopefully this works just fine. I know it looks pretty similar. It's basically the same, same exact type. All right, let's jump in today to 8-4. So 8-4 is really about the idea that the equations that we've been dealing with can be visualized. And we had some of that. I did a little bit of that in class where I showed a connection between the arithmetic sequence and the fact that the common difference was also the same as the slope of a line. That the idea that if I go up one term, I increase by 3 gives us a slope of 3/1. It's the same thing that we would have had if we were graphing it. So I'm not going to start as if you've never seen these things before. All of you have at some point in time or the other. I'll try to highlight a few pieces, but again, some of it may just be a bit of review that you need to dust off. When we talk about um, things in a Cartesian coordinate system, it's named after a particular mathematician. You could also call this a rectangular coordinate system. A couple key pieces. Yes, we do call the origin 0, 0. Otherwise, coordinate points are written with an X component, which is horizontal, followed by a Y component, which is vertical. So horizontal is written first and vertical is written second. There is no good reason why this is, but we had to pick something. And so this is what we've chosen, and it's more like a convention. Okay. We also label things in order as we start. So we would start up here and we would call this quadrant 1, and then we proceed in a counterclockwise motion. So you'll see quadrant 2, 3, and 4. Now, why are we covering this? Again, this is a topic that would typically come up later in uh, in the educational process for some of the kids. Well, we are going to be doing some geometry, and there will be times where plotting points may help us to see something related to the geometry of certain shapes. So having a good basis here is great. Also, connecting algebra, which looks very abstract, right, to a physical graph, which is plotting or graphing the actual solutions to this, which we would call the points on the line. They are really the solutions to an equation. And then we can kind of get a better connection at times. Sometimes it helps us see where two particular lines will intersect, which can give you perhaps a solution to a very specific equation. Okay. Other times it can help us see that there might be infinitely many solutions. So let me go back to one that we did in our opening packet. And I'll jump into Desmos here because Desmos has a built-in graphing calculator. So when we were doing the boys and girls in class, a certain percentage want a party, a certain percentage does not want a party. It was interesting because we end up with a relationship like, I believe it was like, I can't remember exactly, but I'll just say it's B over G equals 7 over 15 or something like this, right? So boys to girls, 7 to 15. Now, when you look at this ratio, it's hard to kind of see what's going on at times. But what you could say is for every 7 boys, there's got to be 15 girls. Okay. So that's one way to think about this. The other way to think about it is to rewrite it so we can multiply both sides by G and get an equation that looks like this, which is exactly the same equation we had, but now we can see this rate of change right here. So if you knew how many girls you had, you could plug that in, multiply by this number, and get the number of boys. As an example, if you had 30 girls, put 30 in for G, 30 times 7 over 15. The 15 and 30 go. So you'd get something that looks like this, 7 over 15 times 30. You could write it over 1 if you want, not necessary. And you'd be able to say, oh, there would be 14 boys for the 30 girls. So what you can do is write that in as a y equals mx plus b. So I could say boys are the y. So y equals 7 over 15 times x. Okay. And what you can see now visually, this is why I'm going to zoom back a little bit just so you can kind of get the idea. What you can see now is, I could drag my cursor along this line and I will always get that relationship. So watch what happens when I hit 30 right on the nose, right? See that? I get 30 right on the nose. And it's like, oh, okay, I see it. I see it. So I could come back and do 15. That would also give me a nice whole number, 15 with 7. Now, this line fills in every other possibility as if we could have fractional number of girls. But this ratio then allows you to see how the number of girls compares to the number of boys. So the next one here, maybe there's one around 90. Okay, so 90 girls, because that would be my input, it would mean that this solution required 42 boys. Okay. So we can see there's infinitely many. I mean, this line will never stop. Like I'll go out here to 1,000, right? So we go out here to 5,000. We could go, oh, what do we want to do? Well, we need things that are multiples of 15, right? So we can find some out here. Oops. Cursor slowed down a little bit. There we go. And we could say, okay, so notice, there we go. 5,460 girls would be 2,548 boys. Okay. So that's the idea in this Cartesian coordinate system. Now, if you are working with Desmos, something else you could choose to do is to use that function notation that we had before. And I'm going to put that right here. Okay. And the reason why this is kind of nice and why you might like it is this is an explicit formula. So what you can do is you can actually type in f of, and then put whatever number in you want. So just think of x being the number of girls, and you could say, okay, well, how many girls do I have? And you might be able to even get away with f of g and put a g in here. Okay, you can. So that means now I can see, okay, girls is the input, boys would be the output. So if I do that, I can come in here and say, well, what about 300? Well, 300 as my input for girls gives me 140 as my output. That's the number of boys. And you could do that for any quantity. So what was it? 5460, 5,460. Perfect. 2548. So this input and output relationship, once you have an explicit formula, can be extremely quick. And that's why it's very helpful for us as we go forward. Okay. All right, so we have ordered pairs. Yes, they can be positive or negative. And you kind of see that as we go forward. Equations of vertical and horizontal lines. Well, if you're picturing a horizontal line, a horizontal line will always have the same y component. So when we write a horizontal line that looks something like this, notice every point on that line has the same y coordinate. Maybe it's a y coordinate of 2. So what we would say is if we want to represent that line, instead of every single point, we could just say, okay, this line is represented by any thing that has a y coordinate of 2. If you have a y coordinate of 2, you are on this line. Okay, and you could picture that then, of course, a vertical line. I'll change the color here. So if we had a vertical line over here, guess what? Every x coordinate is exactly the same. So over here, we could say, okay, this is an x equals -3 as an example, meaning every point that's on this line has to satisfy this equation, x equals -3. So pretty big ideas here. Okay. Now you'll notice if you see x equals 2, you'll notice, but that doesn't tell me what y is. And the reason is it doesn't matter what y is, because no matter what y value you choose, x has to be 2. Now, if you take a look here, this last one is in set notation back from chapter 2. This says, I want the set of all points x comma y. So that's all the points that I can think of. Notice though, x has to be less than or equal to 2 and y has to equal 3. So when you picture that, just read that out loud and tell yourself, wait a minute, okay, I need some points in a grid. I know x has to be less than 2. Okay, so here's 2. So I need all the points that are going this direction, but it's an and statement. So both have to happen. And then it says y equals 3. Well, let's see here. 1, 2, 3. So here's all the points where y is equal to 3. Notice it does include some points where x is bigger than 2. So I don't want those. So I come up at 2 and I say, okay, do not pick this one. I'm going to do an open circle. And let me change even the color here, and I'll make it a little bit thicker, so maybe it's a little bit easier to see. Put an open circle there, and then say choose all the points going that way on the line. So that every point that I've selected meets what is being stated. And that's how you can kind of think of these. And again, I'm asking you to do more thinking necessarily than doing. In previous algebra courses, I have a feeling you were probably told to just do instead of thinking. So I'd rather you think as we go forward. When you get an equation of a line, this is very similar to what we did with arithmetic sequences. And with arithmetic sequences, we came up with an equation. That equation visually demonstrates the slope of the line, which is the increase in y value or output for every unit increase in the input. So if the input goes up by 1, you're going to go up by 3. Now, of course, that means it's a ratio. And since it's a ratio, we could go bigger than that. We could start here and go over 2, 3. We could go over 3 units here. But if we do, then we have to go up in the same ratio. And notice 9 is to 3 as 3 is to 1. This is a proportion back from chapter, oh, please help me, 6, I think 6.4. Okay. All right. Very exciting. So yes, you can go through and graph them. And so for every equation that you are given, for every representation, you can take an x value, you can plug them in, and you can find points. Okay, and now they're going to graph a bunch of them for you here. All I want you to do is kind of take a look at this. Every one of these points has a y equals something times x. That means if x is 0, when you multiply by something, you get 0 out. And that's why the origin is on all of the points. After that, the way these change is utilizing the slope. So if we take this one, which says y equals 1/2 x, in the past, maybe in your algebra class, your teacher said just plug in a bunch of points. I don't think that helps you to see the connection necessarily. So instead, what I'll have you do is pick a point that is on the line right here, the origin, and then use this ratio to find additional points. Okay, so we have to pick things that are in the same ratio. And just remember the change, I'm going to use a little triangle for change. The change in y is on top and the change in x is on the bottom. That might help you to see, what do I do with this number? This is telling you that you need a 1 unit change in y for every 2 unit change in x. So if you go over 2 units, you better go up 1 and you'll find another point. For every 2 units from that point, you go up 1 more. And so you can build it from one point to the next. You could also start at the beginning and go over more than that. So I could go over 6 units on the x. Take a look at what that would mean. That'd be 6 on the bottom. And then how far would I have to go up to maintain that 1 to 2 ratio? And we could say, oh, I have to go up 3. Again, this is the power of fractions with that fundamental law of fractions. So you can use that to find new points very, very quickly. Okay. So that also is pretty cool. All right. Now, you'll notice on the last one they had dashed lines. Dashed lines indicate it's only the points we wanted. If you do a solid line, that means any point that's on the line, even if it's fractions or decimals, would be just fine. Okay. When they ask you to find equations of lines do not have to be that challenging, but whenever you start with the origin, what we just saw is everything that goes through the origin looks like y equals something times x. Everything. Because if x is 0, y is 0. So if they tell you the origin, that's really nice. The only thing I need now is the slope. And so if you pause for a second, you could say, wait a minute, to get from the origin to the point 1, 2, 1, 2, 3, to get to this point, I would go up 3 and right 2. That is a ratio of 3 units in the y to 2 units in the x. And that becomes what goes in the box. Yeah, that's it. That's it. If they give you the origin and another point, it can be very quick. That's your ratio. Okay. All right, let's see here. Let me erase those. They're going to generalize that and say, now let's look at all types of equations. I'm going to jump over to Desmos because I want to show you a tool that you can use with your students as well. And you may never have seen this before. You're welcome to try along at home if you want. But I want you to try this. Y equals, and type in mx plus b. Okay. Now underneath, click all. Now, what you've done is you've created what are known as sliders. A slider allows you to change a value very quickly. So I could change the slope, and you can see what a negative slope looks like. That's really zoomed out. Let me go back and zoom in. To do that, I'm going to go over here to settings. Uh, Actually, I'm just going to copy this and I'm just going to refresh the screen and it'll take me back to the normal window and then I'll paste it. Okay, so there we go. There's kind of the slope. So what I want you to see is the slope is 1, which means if I go right 1, I have to go up 1. If I go up 1, I have to go right 1, the change in y to the change in x. If I bring the slope over a little bit, so now the slope is 2, you can see that it's steeper because I now have to go up 2 units to go right 1, up 2 for every right 1. You'll also notice this other one that we didn't have before. And if you bring it back to 0, it looks like all the equations we just did. So that if I change the slope, it still goes through the origin, every one of them, including negative. So negative, just picture negative as a ratio, -2 over 1. That means I need to go down 2 units to go over 1, or down 2 units for every increase in one of the input. Okay. But watch what happens now to, let me go back to, I'll say 2. Watch what happens to the line as I change the value of b. This is something a traditional textbook really can't do. So you can see what it's doing. All it's doing is sliding, right? Now it's hard to tell whether it's sliding left and right or up and down. But in this case, I can tell you because it says y equals, the value of b is technically impacting the y value. So what's happening is we are moving up or down. Okay, so that as I change that b value, you can see it moves up or down. So what we have here is we have what's known as the slope, and that tells you the steepness, right? How fast is it changing to go from one point to the next? But this other quantity, this b value, is actually just the intercept. Where does it hit the y axis? So when it says b equals 5, you know it's going through 5. Okay. When it says -3, you'll know it's going through -3. You can also click on the line itself and it will highlight a couple of different points that you can find. Those are known as the intercepts. And you notice in this case, I have an x-intercept and a different y-intercept. That's not always the case. Sometimes I'll only have one intercept because they kind of lie on top of each other. All right. Pretty cool. Pretty cool stuff. And that's why I like that visual, so you can kind of see. So basically, any two lines that are not vertical, they're parallel if they have that same slope, because to get from one point to the next, it's exactly the same. And you can see that visually here with the pink, the black, and the blue lines. They all have the same slope of 1. The only thing different is just a different starting point. Okay. Again, terms, we call those the x-intercept or the y-intercept. And we also have the thing called slope-intercept form, which is y equals mx plus b. Pretty standard way of doing it as a very explicit representation. It makes it kind of quick to go through. In any case, any equation that makes a straight line, we call a linear equation. Not a real surprise there. And you can actually see, I mean, some textbooks, depending on who you had for your algebra class, perhaps a long time ago, they might have said, okay, we have y equals mx plus b. That is known as slope-intercept form. And then they also had this other form, which is put all the variables on one side and put the number on the other. Or, again, depending, the authors here are a little bit older, so they have seen this before, and this was pretty common in much older textbooks. Okay. Again, just different ways. Every one of these represents a line. The difference is that the slope-intercept line can only represent lines that are non-vertical. Okay, and why is that? Okay, so let's take a look at a vertical line. Remember, a vertical line looks something like this, and I'll graph it in red. Okay, so we'll go over to x equals 2, and I'll kind of put a little dotted line right here. So I want you to think about that. So if we start measuring what the change is between 2 points, let's pick a couple of points here. I'll pick this point, which is 2, 1, and then we'll go over and we'll pick this point here, which happens to be 2, 3. Okay, so if we were going to find the rate of change, how far these actually moved, we would have to say to ourselves, wait a minute, how far did we change? The change in y over the change in x. Well, let's see here. The y value went up 2. Got it. So that's a change of 2. The x value went up 0. It didn't change. Okay, so 0. And now you might be able to see the issue. We have turned this beautiful idea into 2 divided by 0. Again, this does go back to what we've done in the past. Goes back, I believe, to the first time in chapter 3 where we saw it, but we saw it again in chapter 4, chapter 5, chapter 6. Anytime we had the concept of division, we had to kind of explicitly state what happens when we divide by 0. And so this, as we might recall, is undefined. It is not a defined number because 2 divided by 0, if you go to check it, 2 divided by 0 is equal to some box. If and only if 0 multiplied by whatever's in that box gets you back to 2. And of course, that unfortunately fails. It fails because anything times 0 is 0. So this is always false. So we have this idea that there is no number. We call it undefined. So again, y equals mx plus b works whenever you have a slope. If the slope is undefined, this equation, unfortunately, cannot exist. So that's why sometimes someone might say, well, how come I need 2 different equations for a line? Well, the bottom line right here allows you to have vertical and horizontal lines, whereas the top one kind of excludes the vertical lines. So that's why. And in math terms, sometimes you're like, oh, well, that makes sense. Yes, it's so much easier if we could just use one. But unfortunately, we use one that's like the quick and easy way. And then we have to say, but wait a minute, we can't use it all the time. So we give you kind of a second piece there. Okay. They talk here about determining slope. They say the change in y divided by the corresponding change in x, sometimes called rise over run, rise being a change in vertical, run is a change in horizontal. And they do give you a really fancy equation. I mean, that's fantastic, which is great. I've been teaching now for a long period of time, and I got to tell you, if you just give your students an equation, it will be challenging for them to understand the concept. So you can get to the equation down the road, and maybe some of you do remember something like this, right? Which is fine. This is the slope. You could memorize this. Honestly, you probably forget it. You'll probably mix something up. It happens because we don't use something like this all the time. So instead, let's look at a problem and see if we can use maybe one of Scott's super fast methods as like an understanding the concept idea instead of just memorizing. So let's see here. Ah, here we go. Okay, so it says right down here, given these 2 points, find the slope of the line. Okay, all right. Okay, book, here we go. So what do I have? I have 2 points. Actually, let me get a little white space here just so I can kind of show what I'm doing. Okay, here we go. So I have the point A, and point A is at 3, 1. And I have point B, which is at 5, 4, right? Okay. No, didn't mean to do that. Okay. We're just going to pretend that I did mean to do that and that everything I'm doing right now is meant to happen. I have no idea what I am doing. Okay, perfect. Awesome. So let's take a look. Okay, so now if we were to use the formula, I'm going to show you the formula way first because I know some of you are very much into formulas and maybe you're able to memorize them. Remember, though, you might be dealing with students who can't. They don't have that same skill. Maybe they don't see a connection, so it's harder to kind of memorize. But if you wanted to find the slope, you could come over and use the equation over x2 minus x1. And so you'd find the y2 coordinate, the second coordinate. Okay, so that'd be right here. That's a 4. So that becomes a 4. And the first y coordinate over here is a 1. Okay, so I have 4 minus 1. And down below, then the x coordinates, I have a 5 minus a 3. Okay, so 4 minus 1 is 3. 5 minus 3 is 2. So my slope is 3 over 2. If you want to divide that and get a decimal number, you can. It's 1.5. But honestly, the fractions actually might make it easier for you to see that I go up 3 every time I go right 2. Nice connection. Okay, there's oftentimes students who say, but wait, Scott, what if I switch those up? What if I did it backwards? Okay, let's say this over here is point number 2 and this is point number 1. Let's do the same thing. Okay, so I'm going to take y2. I'm going to do this one in red. Y2, which is now 1, minus y1, which is now 4. What if I had those backwards, like on a quiz or a test? What if I mixed them up? And then over here, I'd say x2, which is 3, and x1, which is 5. 1 minus 4, that's negative 3. And 3 minus 5 is negative 2. And a negative divided by a negative, we know turns out to be a positive. So guess what? We get back to the same thing. So it really doesn't matter which way you do it. The only time you're going to get this incorrect is if you start with a y coordinate here and you go back to this y coordinate, then you pick the x over here and go forward. Then things are not going to look good for you. Then it will be incorrect because you have y2 minus y1, but then x1 minus x2, so it doesn't work out. Now, I said I wanted to show you a way that may be more visual. This way over here, I got to tell you, is pretty abstract. You can't really see these changes. So if I came over and actually graphed the points, here's point A at 3, 1. And the next one is at 5, 4. Okay, there's B. I'm just going to ask you, how far do you have to go up or down to get to B? And how far right do you have to go? Now, again, think of each right or left could be positive or negative. Up and down would be positive or negative. So if I was going from A to B, I would go up 3 and I would go positive 2 in that direction. So my slope would just be up 3 and right 2, which is 3 over 2. Do not need to memorize an equation. You can. You absolutely can. Okay. As a matter of fact, I developed this technique that I think works really well. And honestly, it could have been developed by 600 other people in life. I don't know what everyone else in history has done, but it seems to work out pretty well for a lot of students. So if I start at 5-4 and 3-1, those are my 2 points. Okay. Picture this. Right up on top, right above everything, I'm going to write, how does y change? So to get from 1 to 4, what happens? And you'd say, oh, I went up 3. Perfect. Now look at the x coordinates from here to there. What happened? I went from 3 to 5. Oh, I went up 2. Guess what, folks? Your slope is sitting right there. Okay, so do the y's on top and the x's on the bottom, and you've got it. You're done. They could give you any points they want. Look, here's another one right here. Okay, so now let's try it without the formula on this one. Okay, they say, what's the slope of the line passing through these points? And you're like, okay, great. It's super hard. Not anymore. With Fallstrom's freaking fast technology, we can do this in a heartbeat. And maybe this is what you needed to be like, man, algebra really wasn't that tough. It isn't. It's kind of cool. Okay, let's take a look. We're gonna do the y's on top. So from y to y. Okay. So from 4 to 0, hopefully you say I went down 4. From -3 to +1, that is going up by 2. So that's a +2. There's your slope. And you could simplify it. So you could come down and say, okay, my slope is -4/2, which is the same as -2/1. Okay. And that negative sign actually could go either direction. You want to be perfectly honest. You could write it as -2/1. You could also write it as 2/-1. And graphically, I think that does make sense. But if you're looking and going, how in the world can you just change things around, Scott? Well, watch. Let's see if we can demonstrate it for you so it kind of clicks for you too. If I started at any point at all, okay, I'll pick this point here, and someone said, I want you to use this slope, I could go down 2, down 1, down 2, and then right 1, right? And that would get me a new point on the line. But that's going down 4 or down 2, right 1. Now let's look at the other way of writing this. That has a positive y value. Okay? So now if I have a positive y value, I would go up 2, but the bottom is negative, so I have to go left 1, and I would get another point. So what I want you to see is that you actually create, the points that you create are on the same line. So it doesn't matter which way you're going with the slope as long as you use it properly. Now, don't do both of them negative, right? Because a negative divided by negative would be positive. That's not what we have here. We definitely have a negative slope. All right. Hopefully that really tied some ideas together for you. At least I'm extremely hopeful because I think that's a really kind of a cool way to do it. This allows you to do some things that maybe you couldn't have done before. Being able to convert things between Fahrenheit and Celsius. I know that I've struggled with that in the past, but if I know just a couple of good key points, I actually can use that to create an equation. So I'm going to use the top points and I'm going to use the bottom points. So in Fahrenheit, I would have the points 32, 0 and the point 212, 100, right? That's kind of cool. Okay. So now I'm going to use that technique we just learned. So actually, I'm going to move this point over so that I can find the slope very, very, very quickly. Like, why not? I can find the rate of change. So here we go, right up on top. What is that? Plus 100. What is that? Plus 180. So I now know my slope is 100/180. And if you want, you can simplify that because sometimes the bigger numbers get intimidating. That's 10/18, which is 5/9. Okay. So there we go. Now, if you know the slope and you know one of the points, you can actually find the equation. Let's see how, because I think this is kind of a cool thing. Put in the general equation, m x plus b, and plug in everything that you know at this point. Let's take a look. We know the slope, so that becomes 5/9. And then you can pick, do you happen to know an x and a y coordinate on the line? You choose any one you want. I'm going to choose this one because one of them is a 0. So the y coordinate is 0 when the x coordinate is 32. And then it says plus b. So b is the thing I don't know. But look at what happened. By doing just that, there's only one value, one variable I don't know the answer to. So I could actually solve this to find the value of b. All right. There you go. So that is how you can do it. If you want, you can multiply this out. What is that? 150 plus 10, 160? 160 over 9? I think so. Yeah. So you can simplify that. 160 over 9 equals 0 plus b. So if I'm going to convert, this would actually be a minus 160 over 9 plus b. So now I have a beautiful equation. My y value, right, is Celsius. So what I can do is I can rewrite this now as a final equation. Let me get a different color so I don't mix it up here. Here we go. Celsius, which is my y coordinate, is equal to the slope, 5/9, times x, which is the amount Fahrenheit, minus 160 over 9. Okay. So if I put 32 in for F, I get 0 out. If I put 212 in for F, I get 100 out. Okay. And you could go the other direction. So if you wanted to know, like sometimes you go to another country and they tell you the temperature in Celsius, and you're like, what does that even mean? I'm so used to Fahrenheit. All you have to do is reverse that then. Okay. That's it. All you have to do is reverse that. So there we go. Super cool. Super cool. Okay. Now notice they have factored it out. I distributed, but you could factor it out. And so they've done both ways. They have a Fahrenheit. So if you know Celsius, you would multiply by 9/5 and then add 32. And 9/5 is roughly 2. So if you get into a pinch, you just need a really quick conversion. It's going to be pretty close if you say, okay, I'm multiply by 2. Okay, let me give you an example here, right? So let's just say that you're in a country and they say, oh, it's, I don't know, 14 degrees Celsius, right? That seems like a reasonable temperature. So let's just say they say 14 degrees Celsius, 14 degrees Celsius, right? So if I use the actual formula, I would say F equals 9/5 times 14 plus 32. And now I got to grab my calculator because I don't have that one memorized, and it's going to be probably in decimal number anyway. So 9 divided by 5 times 14, okay, plus 32. Okay, so I can look at that and do it and say, okay, that's 57.2 degrees Fahrenheit. You're like, okay, that's great. But what would happen if I just use my kind of rule of thumb, right? If I use, instead of 9/5, I just say that's approximately 2. I do 2 times 14 plus 32. 2 times 14 is 28 plus 32, and you add those together and you get 60 degrees. And really, if somebody said it's 60 degrees and somebody else said it's 57.2, you're probably going to say, yeah, it's pretty close. Okay. So again, gives you the ballpark, gets you in the ballpark. That's why we learned all that estimating stuff, right? In all the earlier chapters. Very cool. Very cool. All right. Then they talk about a system of linear equations. A system of linear equations is when you have two equations of lines and you can graph the lines and you can see where they intersect. If you are going to do this graphically, it might be good to use something like Desmos. So let's jump in and do x plus 4y equals 6 and x plus y equals 3 in Desmos. Okay, so I'm just going to refresh the page. And here we go. So x plus 4, oops, 4y equals 6 and x plus y equals 3. Okay, so here they go. Desmos has graphed both of the lines, and you can click on the graph and it'll tell you, yep, that's the intersection point. And then just come back and check it. So let's see here. If I plug in a 2 for x and a 1 for y, does it really check out? So this would be 2 for x and a 1 for y. So 4 times 1. And 4 times 1 is 4. Plus 2 gives me 6. Yeah. And down here, 2 plus 1 is 3. Okay, that checks too. So this is how you can find where lines intersect graphically, which is pretty cool. Okay. The book gives you a couple ways to go through and solve these. One is known as the substitution method. One is known as the elimination method. I'll show again. This is up in the grade 8 range. So we're getting to the top of where you would probably see even advanced students in your courses if you're teaching at the K to 6 level. But there are techniques you can use. I look at this and I go, wow, that is intimidating. Like that just looks like a ton of work. There's nothing wrong with this. It just feels long. So while the substitution method is great, sometimes there's other, like we actually did it. We plugged in all the pieces we knew to find B a minute ago, but there's other times where it's not maybe great. The elimination method allows you to add or subtract to remove one of the variables. And I'm going to tell you, if you have a choice, I would recommend you probably get used to doing this one. I think it's cleaner. I think it's quicker. And when you get into solutions that involve fractions, you may be able to just eliminate twice to get the final solution. Okay, let me go ahead and show you on this one what I'm talking about, because right there, it kind of looks a little bit intimidating, like having a system of equations. But what we're going to do is we're just going to go ahead and write those up here. 3x plus 2y equals 5, and 5x minus 4y equals 3. All right. All right, here we go. What's the idea? The idea is to eliminate some of the variables. In order to do that, go back to your skills from chapter 4. We need to find common multiples. Which one do you want to get rid of first? So maybe you say, I want to get rid of the y variable first. Awesome. Look at the coefficients, a 2 and a 4. Find a common multiple of those, and then use that common multiple to scale up each individual equation. So between 2 and 4, you might be able to say, oh, Scott, the least common multiple is 4. Perfect. So I'm going to leave the bottom equation alone because it already has a 4 in it. And then I'm going to scale the top up by 2. So I'm going to multiply everything by 2. So 3x times 2 becomes 6x. 2 times 2 becomes 4y. It stays positive. And 2 times 5 becomes 10. There we go. Now, it seems like you're like, wait, that's it? We're like one step away from being done. So take a look here. Because one is positive and one is negative, if I add them, they will eliminate each other. Elimination. The eliminator. I'll be back. So eliminate the y's by adding these together. Now, of course, if they were the same sign, don't add them together, subtract them. That's it. That's it. So 6x and 5x gives me 11x's. 4y plus minus 4y goes away, and I'm left with 13, which means x is 13 over 11. Okay. Haha. Now you have choices. If you were back in your algebra class, most likely, this is for about 90+% of American teachers, they would have taught you the technique of put this back into either one of the equations over here. And there's nothing wrong with that technique. Okay. All you have to do is not make any mistakes when multiplying, dividing, and subtracting with fractions. Okay. So the difference is that American students tend to make most of their mistakes when they're adding, subtracting, or dividing with fractions. So my recommendation is to just come over. This is, I think it might be even easier for you. If you've struggled with algebra in the past, you're like, I keep getting it wrong. I got like part of it right, but not all of it. Just try this one. You may find that you don't hate algebra as much as you thought you did. It was just the way they told you you had to do it. All right, here we go. So now I'm going to come over here, and what I'm going to do is I eliminated y before. Now I'm going to eliminate x and see if that makes a difference for us. Okay, so I need a common multiple of 3 and 5. Okay, common multiple 3 and 5. The least common multiple would be 15. Okay, so that means I need to multiply the top by 5 so that I get 15 x's. Okay, see them there. And then I have 5 times 2 y's. So 5 times 2 y's would be plus 10 y's. And 5 times 5 is 25. Then at the bottom, I'd have to multiply this one by 3 to bring it up to have 15 x's, because 5 times 3 is 15, and then multiply every other piece by 3 as well. So minus 12y equals 9. And if you're ready for it, here comes the twist. I need to eliminate the x's, so I need to, in this case, I need to subtract. So I'm going to subtract. Now, if you want to go a different technique, some teachers will say, well, if you have both positives, do one multiplied by 5, the other multiplied by like -3. You could do that if you want. I'm fine with doing subtraction though, so I'm going to be over here. 15x minus 15x gives me 0 x's. The x's are now gone. 10y minus -12y. Subtracting a negative. Hey, that's the same as adding the positive. So that becomes 22y. And on the other side, 25 minus 9 becomes 16. My end result here, when I divide, will give me y equals 16 over 22. Or if you want, you get 8 over 11. So there's your y coordinate without having to go back and do a ton with fractions. Your solution would be the point right here. X is 13/11 and y is 8/11. And now you don't feel that intimidated by fractions. You could grab your calculator and plug those in to check and make sure they actually do work. I'll do one of them. I'm not going to do both of them, but just to kind of show how would I do that. So I'd have 3 times 13/11 plus 2 times 8/11, and that has to equal 5. 3 times 13/11 gives me 39 over 11. 2 times 8 gives me 16 over 11. And my final result, when I do add those together, is 55 over 11, which simplifies to 5. That's meant to be like a firework, because that's kind of cool when you get it right. Okay? You just check it in both of them, and you know guaranteed you got the right solution. That is how we do it. Okay. Now notice this is the fun part. I love when authors write this out. Like, oh, okay, just do this quick and easy thing. So what they say here is go ahead and do the solution very similar to what we did. We got 13/11. They got 13/11. Then they say to find the corresponding, we substitute this for x in either one of the original equations. They don't show that, right? They didn't show any of it. They're like, and here's the answer magically. So anyway, I wanted to give you a stronger sense of why we do what we do. And also, as you look at approaches to solving problems, that you may really want to try to find the most efficient one and the one that may minimize the mistakes that your students make, even if what you do ends up not going with exactly what the textbook says. Just as a point. All right. There are times where you use our wonderful techniques and you get something that looks really, really, really weird. So when we did it, we got x equals 13/11. But it's possible that you can end up actually eliminating everything. So like x's and y's get eliminated. And that can happen. And down here, we actually saw this happen. Here we end up with 0 equals 7, which I hope in your mind you are screaming, false. That can't happen. Okay, so what are we trying to do and why did this happen? Here's what happened. If I take a line and I say, where does that line intersect with this line? You will be able to find a point of intersection. But if I just give you two lines and I say, where do they intersect? The techniques that we were doing is what we were saying is, okay, These points will intersect when, and then we found the solution. So previously we said the lines would intersect when x was 13/11 and y was 8/11. That's when they would intersect. Well, when we just did it here in this example, these lines will intersect when the 0 equals 7, right? But that means like that will never happen. 0 will never equal 7. So if you are given two lines and told find when they intersect, and you find that they never intersect, you know something about those lines. You know those lines never intersect. And that is what we call parallel lines. Okay. Uh-huh. Now, it's also possible for you to get down to the bottom, not a 0 equals 7, but to get a 0 equals 0. That's possible. That means the x is canceled, the y is canceled, and the number's canceled. Okay, so picture that. These two lines will intersect when 0 equals 0. And hopefully you're saying true, or you're saying that always happens because 0 always equals 0. And then you'd be 100% correct. Because what they did, maybe accidentally, is they gave you a line and they asked, when does that line intersect with this line? And then they put the other line like right on top of it. And then you could say, well, wait a minute. Wait, well, this point is on both, and this point is on both, and this point is on both, and this point is on both. So you're really just saying every single point that we have on any of the lines is a solution. And you are, once again, 100% correct with that. So it's possible for you to get lines that have a 0 equals 0. And I just need you to interpret that and say, oh, that's always true. So it must be always true that these lines intersect. If you get a 0 equals 7 or a 0 equals 5 or something that you know is always false, you should say, then these lines can never intersect because that equation is never true. If you do get a single value like we did earlier, then you'd be able to say, oh, they intersect at one point. And that's exactly what's happening. And that's what we have with equations of lines. We have kind of three situations. Notice they go through and give you a couple opportunities. They say, hey, try all of these. Okay, that's fine. We could use our techniques that we know about to try some of these. Maybe I'll do one of these. Maybe I'll do the one. Oh, and by the way, anytime you see fractions in an equation, I know sometimes people are like, oh my God, it has fractions in it. Just take a breath. Find the least common denominator and then multiply that by every number. And you can just rewrite it so it doesn't have fractions. If that makes it easier for you, then go do it. So see down here that the least common denominator would be 2. Multiply every number by 2, and I'd get 1x minus 2y equals 2. That's the same line that we started with. And now I can keep the other one I started with and say, okay, we're good. I can solve that. That might be easier for me. So like here where they give you this as a 3 and a 4. Well, the least common denominator is 12. So multiply everything by 12. So this would be 12x divided by 3, which gives you just 4x. 12y divided by 4, which is 3y. And 12 times 1, which is 12. So again, don't have to make this more complicated for yourself. You can make it easier. To me, I like this approach. Then I'd come down to this one and I'd solve. So I'd make it simpler by taking one extra step, I know, but I wouldn't have to deal with fractions, and that's when I tend to make mistakes. Even me, I know, because fractions are a little bit more complicated. Let's try this last one and kind of see what we end up with together. So 6x minus 9y equals 5. Underneath, they have negative 8x plus 12y equals 7. Okay, I'm going to give us some white space. And here we go. Again, for many of you, what I'm doing now is I'm trying to go in depth on pieces you may have struggled with in other math classes. Please understand, you may be fully good with your algebra. That's the prerequisite for 105 and 106. So if you're in that boat, you're good. Okay. All right. So let's see here. Let's try this together. So I want to eliminate something. Take my pick. Why don't maybe I'll eliminate x's first this time. Okay. So I need a common multiple of 6 and 8. Okay. So common multiple of 6 and 8. I can use any technique possible. I'm going to do prime factored form. 2 times 3. This is a 2 times a 4. So a common multiple has to have a 2, a 3, and a 4. So 4 times 3 is 12, times 2 is 24. Okay, so my common multiple here would be 24. Got it. So what do I need to make 24? Well, 6 times 4 gives me 24. 24. 4 times 9, 36. And 4 times 5 is 20. Down here, to get 24, I would need a 3, because 3 times 8 gives me 24. 3 times 12 gives me 36. And 3 times 7 is 21. And then take a look. 24x minus 24x, I could add these together and they will eliminate. Love it. So 24x minus 24x, if I just add these two equations together, those go away. So I have 0 x's. Negative 36y plus 36, that gives me 0 y's. And over here, I get 41. That means I end up with 0 equals 41. And over here, you could say this never happens. And then go back and ask yourself, well, wait, what the heck were we doing anyway? I was asking you when these lines intersect. And you would say that never happens. And two lines that never intersect would be parallel lines. There we go. Done. That's it. You have the power. So there you go. You have the power. Okay, so then they give you okay, then they give you different ways. So they do talk about how you can use these techniques to solve multiple equations if you need to. I think for these, if I'm dealing with the age group that you might be dealing with, then like I might use a different technique entirely. So let's solve this problem, but I'm not going to solve it the algebraic way. I'm going to solve it the algebraic thinking way. Okay. Okay, at a local farmer's market, people bought different things. So let's see here, cantaloupes, vases, and watermelons. All right, cantaloupes, vases, and watermelons. So if you're looking at that, then you could create equations that says a cantaloupe, that's, I don't know, writing in white, that's not going to go well. Cantaloupe plus vase is 8. A watermelon plus a vase is 9, right? I mean, you could go through and do these, but there are a couple ways you could do it visually, and especially when you're working with younger kids, that might be even easier. So I'm going to draw a cantaloupe. Okay, cantaloupe is kind of a yellowish orange. I don't have that color. So we're just going to pretend that this is cantaloupe color. All right, there's a cantaloupe. Okay, a cantaloupe plus a vase, a vase. Okay, and there's a beautiful handmade vase. Almost looks like a graduated cylinder in chemistry, but it's a vase. Okay, because I built it. Okay, and that is worth $8. Underneath we have another vase that is identical. There we go. It's totally identical. That looks like a nose, like a cartoon nose, but just go with it. And then we have a watermelon, and watermelons are big. Okay. Okay, and then at the end, I have a watermelon and I have a cantaloupe. Okay, so if you now put a price with each of these, you could say, okay, this is $8. The next one is $9. And the last one is $7. Okay, you could actually get to the solution without involving algebraic variables, equations. But let's see how, and kind of maybe if there's a kind of a quick way we can do it. So picture in your mind that we decide to maybe group some of these together. I'll show a couple different techniques. Let's say you want to group these together. So you push these two orders together, right? So now the 8 is gone, the 9 is gone because now you bought two vases, a watermelon and a cantaloupe. And you could say, okay, now 8 plus 9, that gives me 17 for that whole pack. And what I want you to see is that you have a watermelon and a cantaloupe, and you know those are $7. So what you have is right here, you know this portion is $7. So you could come off to the side and just say, wait a minute. That means that my two, these are horribly drawn. They don't even look like vase. I don't know what they look like. Just it's a vase for I expect your drawings to be as good as this. That's the level. So what I'm saying is I have two of these vases and that's got to get me $10. All right. And at that point you could be like, oh, a vase is $5, right? That's it. Then you're done. Because after that, everything else, in a sense, falls apart. Why? Because I know that a vase plus a watermelon is $9. Oh, okay. The watermelon must be $4 then, because a vase and a watermelon is 9. And I know that the vase is 5, but a cantaloupe in a vase is 8. Oh, okay. So a cantaloupe is $3. And see, you're done. I didn't use variables. I didn't use any of that. I used some thinking and kind of how I would combine things together, but that's it. Yeah, there you go. And that's the way you could do it. Okay. I said I'd show a couple ways. I'll show a couple ways. So hopefully that makes sense. You're like, wow, I could actually do some things to create a new equation. Absolutely. But what you may not see, and the student may not see yet because they may not be ready for it, is we actually did the elimination method here. So by adding two equations together, we create a new equation. Then by kind of taking out the melon and the cantaloupe, we would have subtracted another equation to create a fourth equation along the way. So that's the idea, maybe a fifth equation along the way. Okay. All right, let's go back. I'm going to just undo all of this. Okay. Now, here comes the fun, right? Okay, so what do I know if I want to solve this a different way? Okay, first off, looking between these two, I can see what? I can see that the vases are the same. So I don't know how much a vase is, but they're the same cost. Okay, so whatever it is, vase plus cantaloupe and vase plus watermelon, the watermelon must be $1 more than a cantaloupe. Okay, so I'll jot that down. Now looking at this last one down here, remember a watermelon is $1 more than a cantaloupe. So if I traded out the watermelon, I could trade it for, oops, let me go here, for a cantaloupe plus $1. So I could get rid of this watermelon. Now I have a cantaloupe plus $1 plus another cantaloupe. Well, why don't I just get that dollar out of here? And I could say I now have two cantaloupes. And because I gave the dollar away, I have two cantaloupes are going to cost me $6. Guess what that means? One cantaloupe is $3. And once I know a cantaloupe is $3, I can go back up here and say that's $3. Well, then the vase had better be $5. If the vase is $5, then the melon better be $4. Or once I know the melon, $1 more than a cantaloupe is a watermelon. I know the watermelon's $4. So you can get to the answer without using all of that algebra. Sometimes teachers really want you to show the algebra because they're trying to get you to practice algebraic work. But in this class, it's more about algebraic thinking. So I hope that you take that into consideration as you get into the homework. There are more than one way to do these. If you want to practice your algebra, you can, but you can do algebraic thinking and get to the same result. And I know this one was a little bit longer. It's for those of you who might be rusty with algebra. If you're good with algebra, you probably could have done a ×2 speed because you're like, I got this. I know how to find the slope. I know the equations. All of that is great. Just doing a little bit more for those of you who might be a little bit further away from when you have done algebra. All right. That's it for now. Off you go.